All right, good afternoon, everyone. Before we start, I think I'll give you a little bit of a background on what I've been doing the last 50 years. Uh, my meteorology experience goes way back to 1968 when I was an ensign in the Navy and found out about a program just as I was starting my first duty station that the Navy needed some new meteorologists, and anybody with a science or math background, they'd send them out to the Naval Postgraduate School in Monterey, California, and give us all the basic weather courses that we would have had if we were meteorology majors. So I was a chemistry major, so I qualified. So I went out there and I went through the year intensive course, and so I was an official professional meteorologist in June of 1969. And so I spent the next 5 years in the Navy forecasting in various places, including Keflavik, Iceland. So I had a chance to forecast weather for the whole North Atlantic region, including all of Europe, North Africa, all of North America. And after that, I went and I got a master's degree in meteorology at Rutgers University. And I got a job working for a private firm in the Boston area. And at the time, in 1976, we were the main competitors for AccuWeather. And they were actually afraid of us because we were moving into all their territories as far as radio stations and other clients were concerned. But the trouble was our management was trying to undercut AccuWeather's prices. So they were practically giving away our services, and we went bankrupt. So at that point, in 1982, I got laid off, and Judy and I moved up here to Maine. And I wasn't a meteorologist anymore, at least at that point, but I found out about some teaching positions at Dexter High School, and I was teaching math and science there until 2001, when I finally decided I had enough of that and I wanted to get back into weather forecasting. So I started my own business out of my house, and Pat and Kim are two of my clients, and they know what I do every day. And the first thing I'd like to show you today is because we're inside, and the reason that we're inside is because there's a chance for some thunderstorms moving through, and we didn't want to take a chance on the equipment getting wet, and if you have thunder, then there's lightning, and that gets dangerous. So I just wanted to show you why there's a chance for some thunderstorms before we start the actual slideshow. And this is a sequence of radar shots. Now this is 14:20, that's Greenwich Mean Time. So you subtract 4 hours, so that makes that 10 o'clock this morning, 10:20 this morning. And you look back here and you see these green and yellow shaded areas, and these are showers that have already developed. And usually where you have yellow and sometimes red, there's some thunder that's involved with those showers. And I'm going to show you the sequence here over the next few hours. Now notice how the movement is up along the mountains and the Quebec-Maine border here from northern New Hampshire. All right, now, see this area here? This is the one that concerned me when I first came in about 12:30, because it looked like this thing could move right over. See, here's Dover Foxcroft right around here. And it looks like this blob right here could be moving right at us. However, since that time, it's tending to move more this way, north of Greenville. So at least at this point, I think we're not going to see that blob. However, if you look back here over New Hampshire, you see that there are more forming. And as long as the atmospheric situation is the way it is over us, there's still a chance that one of those could develop and give us something. So it's a good idea that we're inside today. Okay. beginning. Now let's see if I remember. All right, I'm calling this the climate of central Maine at the present and the likely future. And as you probably know, global warming has been having an effect on climates worldwide. The effects have really become more noticeable over the last 10 years. But it's something that it's probably, the transition to a new climate state has probably been going on since the 1980s. Only it's just accelerated as time goes on. No? Okay. Now, as far as what drives the climate, these are the main things that cause the climate to do what it does. The first thing, the solar output. That should be obvious to most people. We get all the energy for everything that happens here on Earth from the sun, or most of it. There's a little bit from the Earth's mantle and what's going on below the surface, but that's very minimal compared to what the sun gives us every day. The other thing that's important are the orbital variations, the so-called Milankovitch cycles. And we give them that name because Milankovitch, who was a Serbian mathematician during World War I, had the idea, after he had studied various changes in the Earth's orbit because of the influence of the other planets, mainly Jupiter and Saturn, tugging at the Earth's orbit as it goes around the sun. And so over the years, there are these cycles where the orbit actually changes slightly. And so it'll change in very small amounts how much of the sun's radiation actually gets to the Earth. And we can see that in the next slide. Well, first let me go back, because this is kind of like a brief overview first. The other thing is the Urus Albedo, or the amount of the sun's radiation that gets reflected back into space. And that's usually caused by very white or bright surfaces, such as the polar ice caps, clouds, desert areas that are very light, so they tend to reflect the solar radiation back. Most of the oceans, the open water, are very good absorbers of the solar radiation. So when you're out over the ocean and there are clear skies and the sun's just beating in, most of that radiation is being absorbed by the oceans. And this also goes for dark surfaces on land areas. So forested areas, jungles, intensely cultivated areas, all those places would be good absorbers of solar radiation, and you wouldn't have as much reflection. The next thing, greenhouse gas concentrations. And right now, this is becoming the dominant player in what's going on. Greenhouse gases have been a player in Earth's climate right from the start. And the thing that most people don't realize is most of the atmosphere is made up of gases that are transparent to both solar and terrestrial radiation. What comes in goes out. However, there are certain trace gases, and I'm going to show you what they are in a minute, that they actually absorb a large part of the terrestrial radiation that the Earth wants to radiate back into space. And because they absorb it, then they can re-radiate it back to the Earth's surface and keep the surface warmer than it would be without them. And if it weren't for those greenhouse gases, we would be just like the moon. In other words, too cold, everything would be frozen. The parts of the Earth where the sun was shining, the temperature would shoot up, but then it would plunge at night because there's nothing to hold the heat in. And that's what happens on the moon. If you were an astronaut on the moon, you'd probably get up to 170 degrees during the day, and you get down to 170 degrees below zero at night. That's, I'm just throwing those numbers out, but it's approximately what you'd see. A very extreme condition. And obviously you couldn't have any life forms surviving in that type of environment. So without those greenhouse gases, that's what Earth would be like. And we've had them since the beginning when life first formed about 4 billion years ago. And we've had liquid oceans at least since then. And these greenhouse gases have enabled Earth to be warm enough to support the liquid oceans and to keep the conditions good for life forms. And finally, we have the position of the continents and the ocean currents. And this factor, or these factors, they're very slow acting. And it's something we didn't even realize until the idea of plate tectonics came into play during the 1960s and 70s, when scientists finally realized that the continents don't just stay put, they move. And the shape of the oceans change. And this has been going on for millions and millions of years. And that's because the crust of the Earth slides over a molten mantle. If you were to go down, say, 50 miles below the surface, in most places you'd be into the mantle. And if you've ever seen a volcanic eruption, you know what the mantle looks like. All that lava that comes out of a volcano, that's what it's like if you go down 50 to 100 miles. It's very like a jello-like consistency. Things can slide around on it very easily. And these motions that occur in the mantle are what cause both the continental plates and the ocean plates to move around and change the shape of the continents and the oceans. And also, the oceans, because they're fluid, just like the atmosphere, when you have disparity in temperature, you're going to have motions. You're going to have currents forming both in the oceans and in the atmosphere. And so the shape of the oceans has a bearing on the direction of those currents and where they're going to go and how they're going to bring colder water if it's coming from the pole towards the equator, or warmer water if it's coming from the equator towards the pole. So those are the 5 main things that affect the climate. Now, the first thing, the solar input, and you can see, you probably saw a picture like that when you were in grammar school, how the sun's rays, more or less, you can say that they're parallel, because when you're looking at the distances out in space, even though solar energy goes out 360 degrees in all directions, because the Earth is so small compared to the sun, you can make the approximation that the rays are coming parallel. So you know that most of the intense radiation is near the equator, and just glancing blows near the poles. And we're about halfway at 45 degrees north. Now the solar output, if you were to average it over the entire surface of the Earth, it comes to about 2 calories per 2 calories per square centimeter each minute, and that turns out to be about 1,394.3 watts per square meter. And as I say, that's the average. That's what would hit the top of the atmosphere. So we say 100% of that hits the top of the atmosphere, but not all of it makes it to the surface. When you get to the surface, you get just a little over half on average that actually makes it to the surface. You get some of it gets reflected back into space. The average is about 30–35% gets reflected back either by ice caps, clouds, or light surfaces. Some of it gets absorbed by the upper atmosphere, mainly the ozone layer in the stratosphere. About 9% gets absorbed there. And then the rest will get absorbed by the surface. Now, any body that absorbs energy is going to emit it back into space, or emit it away from itself. And this is standard, if you know anything about energy transfer, how radiative effects occur. Anything that comes in is going to go back out. That's just the way the physics of it is. Now, it's not going to be the exact same type of energy that goes out that came in, because that energy is going to do some work before it goes back out. So the energy that the Earth emits back into space is going to be less intense, and it's going to be at a higher wavelength. And we say that most of the solar radiation that comes in is in the visible spectrum, and most of the radiation that goes out from the Earth is in the infrared spectrum. And if you have exactly the same going out that came in, the Earth's climate is going to stay pretty even. It's not going to get warmer, it's not going to get colder. The changes occur when there's an imbalance occurring with that energy transfer. What comes in, if it's more than what goes out, we're going to warm up. If it's less than what goes out, we're going to cool down. So that's it in a nutshell, what causes the climate to change. Now, there are different factors that make those differences occur, and that's what we're going to get into now. The first thing I mentioned are the Milankovitch cycles. This is an idealized picture of the Earth's orbit around the Sun. And right now, it's slightly elliptical. But it varies over the course of about 100,000 years from almost a perfect circle to an even more elongated ellipse. And it should be obvious that if you have an ellipse, there are going to be times when the Earth is further away from the Sun and times when it's closer. And that's going to affect how much solar radiation comes in. There are other wobbles and fluctuations that occur. One of them is the tilt of the Earth's axis. Now it varies. Right now it's about 23.5 degrees off center. And it varies from about 21.5 to 24.5. And the more of a tilt you have, the more extremes you're going to have as far as the sun radiation coming in. If you think about where we live here at the 45th parallel approximately, you know that you can watch the sun in the course of the year. In December, it's very low. It comes up over there and then sinks over here. And then as the year goes on, it gets a little bit further to the east and gets a little higher. And then right now in the summer, it's almost overhead. And the more of a tilt that you have, the more extremes those changes are going to be. And if it so happens that the northern hemisphere, at least at this point in the Earth's history, if the northern hemisphere gets more heating in the summer so that any ice that's around will melt, then you're going to have a warming climate. Because, for example, the ice cap that's over the North Pole right now, that's kind of like our cooling system for the northern hemisphere. And if it's not there, then we don't have a cooling system. It's just like you shut off the air conditioner, and then you're stuck with the heat. And so that's what can happen when you have a very extreme tilt in the Earth's atmosphere, if it so happens that the summer northern hemisphere or if the northern hemisphere is with the extreme tilt during the summer. Now, if the Earth is more in a circular orbit, then that extreme isn't as great, because Earth will be pretty much the same distance as you go around. The other major change is the wobbling of the axis. And by the way, the tilt, that's about a 42,000 year period with tilts like that. And then the wobbling of the axis, you know, like a top spinning, you'll see the axis kind of spin with it. that takes about 21,000 years for a complete change. And you can look at it, we know that today the so-called Polaris or North Star is just about due north if you look up at the night sky and you know where the Big Dipper is and Little Dipper, and you can figure out where Polaris is. Well, in another 10,000 years, it's going to be towards the star Vega. That's going to be due north. And then 10,000 years after that, it's going to be back at Polaris. So that's because the North Pole is wobbling over that 21,000 year period. And this has a very subtle effect on the amount of radiation that comes in from the sun too. Not as great as the other two factors, but still it plays a role. Now when you combine these three, it turns out that there's about 120,000 year cycle that occurs where you have more heating for a relatively brief period, and then the temperature goes way down and you have an ice age. And then it goes back up again, and you get into what's called an interglacial, and then back down again, another ice age. And this is about a 120,000 year cycle. And we've recorded these looking at both the Greenland and Antarctic ice cores that show us that this is actually happening. In fact, this is how they figured out that Milankovitch's ideas were true. Nobody believed them back in 1920 when he published this. But over the years, as they did more research and then they finally got the ice cores out, they saw that, yeah, this matches it perfectly. So now we know what caused the comings and goings of the ice sheets over the last 3 million years of the Pleistocene epoch that is highlighted by these ice ages. Before that, we really didn't have any ice ages for a long time. So it's only been for about the last 2.5 to 3 million years that we've had these cycles of ice ages in 120,000 year cycles. And it turns out that the interglacial that we're in now, it started about 12,000 years ago. And during that time, we started a very gradual cooling trend. And it was probably climaxed with the so-called Little Ice Age that occurred from about 1650 to about 1850, around that time period. And you probably have seen historical records of colonial times when everything froze up in the winter and there were mountains of snow everywhere here in New England, and that's where some of the legends of winter weather in this part of the world came from, because it was true. Back in colonial times, winters here in New England were very harsh, and that was because of the Little Ice Age. Now, most climatologists today agree that that Little Ice Age was just a forerunner of where we were headed, because most of the interglacials only last about 5,000 years at the most. And this has been an exceptional one because it's been over 10,000 years that we've had this relatively mild climate. So we were due to start cooling off again. So within about the next 30 to 40,000 years, we were going to be back in another ice age. However, things changed. Let's just quickly talk about Urus Albedo, which is how much gets reflected. And you can see quickly here the oceans absorb up to 90% of what the sun is putting out, or whatever reaches the surface. And then white snow and ice reflect about 90%. And that's one reason why the poles tend to stay very cold, even during the summer. Light land surfaces tend to reflect. I already talked about that. Dark land surfaces tend to absorb. Clouds tend to reflect up to 90%, especially low clouds. Right now, we've got some medium clouds and some high clouds. If all we had were high clouds, there wouldn't be much reflection. But if you have a very thick layer of low clouds, most of that solar radiation is going to be reflected. Vegetation tends to absorb and hold the radiation, and because of all the water in the plants, it can hold a lot of that solar heat. So even though you feel cooler when you're in the woods, in reality, all those trees and all that vegetation is absorbing a lot of the solar heat. You don't feel warm because the heat is being absorbed and held by the water. It's just like if you go into a lake right now, you'll feel cooler. But there's an awful lot of heat in that water because water has such a high heat capacity. You don't feel it because most of the heat goes into being absorbed by the water. It doesn't change the temperature that much. And that's another reason why if you live near the water, especially near the ocean, your climate tends to be more even than if you live way inland, because the water can hold so much heat. And bare ground, human infrastructure, tend to act like a desert, and they tend to reflect a lot of the incoming solar radiation. And depending on the color and just what's part of that infrastructure, that'll say just what percentage actually gets reflected. Now, greenhouse gas concentrations. This is where the big changes have occurred. Now, this chart that I have here goes up to 2011. See this thing right here with carbon dioxide, CO2? Back then it was 391 parts per million. We're up to 415 now in 2022. And I'll show you a chart later on that shows just the inexorable increase in CO2 that's been going on. The other greenhouse gases, and I want to point out that these three, methane, CH4, nitrous oxide, N2O, and water vapor, H2O, are all much stronger absorbers of infrared radiation than carbon dioxide is. However, these three are more ephemeral. In other words, they're more, especially the methane, it's very reactive. Most of the methane that gets put into the atmosphere eventually ends up as CO2 because it oxidizes with oxygen and forms CO2 and water vapor. And the nitrous oxide is actually the greatest absorber of infrared radiation. It has almost a 300 times as much effect of absorbing infrared radiation as carbon dioxide. But luckily for us, there's not that much of it. So you can see parts per million, it's actually less than 1 part per million. So that's good for us. Now, water vapor, which is also an excellent absorber of all kinds of energy, not just infrared energy, it's very highly variable. And the reason for this is that water, the Earth's temperature structure in the atmosphere is such that you can have water in solid, liquid, and gas, and they can do it all together at the same time. So the water vapor itself, which is a very good absorber of infrared radiation, a lot of times won't last very long. It'll condense and fall out as rain. And then you have dry air, no more water vapor. So the fact that these three can be changed very quickly. The residence time over here, luckily again, because the nitrous oxide can be over a century, but the methane, the max would be about a decade. And after that, it gets transformed, either comes out or it gets transformed to carbon dioxide and water vapor. The CO2 will last for a century without changing. It's a very stable molecule. And the fact that it's very stable and has a very long residence time is what makes it so important. And that's why it actually, even though it's the weakest of the 4 major greenhouse gases, it becomes the most important because it's very stable and it lasts so long. Now, there are a few other trace greenhouse gases like chlorofluorocarbons that humans put into the atmosphere, but especially since they've been outlawed, we don't have to deal with them very much. Now, I just want to quickly show you what's called the fast carbon cycle, and then after I'll show you the long, slow carbon cycle. If humans weren't doing what we're doing, more or less year to year, the balance between the carbon that goes into the atmosphere and the carbon that comes back to the surface would be more or less in balance. Now see where the red spots are. These are human contributions. See here from a power plant, and this here is from agriculture, and here from what we're doing in the oceans. If humans weren't here doing what we're doing, you'd see everything would be yellow, and what goes out into the atmosphere and comes back to the surface would be in balance. And that's what usually happens over the course of millennia if we weren't doing what we're doing in our civilization. Over time, a lot of people that are kind of skeptical about all this say, well, we've had ice ages and heat waves in the past, and humans weren't around. Yeah, but other things have been happening. The main cause of CO2 in the atmosphere is volcanic eruptions. And these don't happen all the time, but over time they will add to what goes into the atmosphere. Now, usually the cycle will take the CO2 that goes into the atmosphere, and it'll be absorbed by the oceans and used by the biosphere in their daily lives. And when they die, all those things will drift down to the bottom. They become part of the bottom of the bottom of the ocean, and eventually they'll be drawn down and become part of the mantle, which then gets sucked into the because of the plate tectonics, sucked down into the mantle, and then add fuel again for the next volcanic eruption. Now, you got to think about this in terms of millennia and millions of years. And this is what's happened in the past when we've had very warm climates and very cold climates. In fact, there have been some periods in Earth's history where it's been cold enough because of a lack of CO2 in the atmosphere, where we've had what's called Snowball Earth situation, where the entire planet was covered in ice. The first time this happened was about 2.5 billion years ago. And they attribute this to the fact that this is when the first photosynthetic organisms evolved, the cyanobacteria. And because they used the CO2, they took it out of the atmosphere and released oxygen. This is the cycle that we see with plants and animals today. The plants take CO2 out of the atmosphere, release oxygen. Animals will take the oxygen, release CO2. So it keeps a balanced cycle there. But because there weren't any animals around 2.5 billion years ago, the CO2 that kept being taken out of the atmosphere wasn't being replenished. So eventually it got so cold that the ice sheets started spreading from the poles and reached the equator. And the whole planet was covered in ice, just like Jupiter's moon Europa is today. Now eventually the volcanoes were still erupting. And so if you've ever been to Iceland, you'll see volcanoes erupting under the ice sheets, under the glaciers that are in Iceland. And this was going on worldwide. So after a few million years, with all the volcanoes going off under the ice, they'd be poking up through, putting more CO2 back into the atmosphere. So eventually, you went the other way. It got warm enough so that it would melt all the ice, and we went into a hothouse Earth, because there weren't any mechanisms to reduce the CO2 until animals came around and pulled the CO2, or animals came along and made a balance with the plants. And that's what happened around the time of the Cambrian explosion, around 542 million years ago. And all of a sudden, all the different life forms that we see today started evolving. And that's another thing to remember, is that life forms on Earth are an integral part of the climate system. And the reason for this is because of this carbon cycle. And also involves the nitrogen cycle and the phosphorus and a few other mineral cycles. But the things that regulate the climate, they do so with inputs from all the living organisms that exist on Earth. So that's why we call it the climate system, because all these things are contributing to how the climate balances out in any particular time. Now, the last thing in that first list I showed you, the influences of the shape of the continents and the oceans. Now, in general, now this is a very rough estimate, if you have continents at the poles, you tend to have a colder Earth. And that's because continents at the poles will tend to retain snow and ice. And snow and ice, the more they grow, the more you end up with what's called a positive feedback, that the more snow and ice you have, the more you're going to accumulate on it, because it won't melt if it's up at the pole. If you have oceans at the poles, which we don't really have right now, because even the North Pole, even though the Arctic Ocean is right over the pole, it's surrounded by very high latitude land. And that's why the North Pole, up until recently, has had a continuous ice cap over that whole area. And obviously in the Antarctic, it's all continent centered over the South Pole, so there's always snow and ice there. If a continent is at the equator, which is what happened, say, 350 to 250 million years ago, you have a very, very warm climate. And that's because the continents will absorb a lot of that energy. And you'll have oceans on either side of the climate going towards the pole, and they'll absorb even more energy. So there's really no place where you can have a cold building effect the way you can if you've got continents at the poles. Also, if you have a continent at the equator, you tend to have a drier climate. And that's because most of the evaporation that takes place is near the equator. And if you've got a continent, there's no water. So you've got to have at least some water near the equator or in the tropics in order to have enough evaporation to give you a more humid climate. High latitude oceans tend to be warmer than the adjacent continents, again because water can absorb so much heat. High latitude continents tend to be colder. So for example, we can just look at the way the Earth is situated today. In the northern hemisphere, where the majority of the land surfaces are, the northern hemisphere tends to be colder on average than the southern hemisphere. And that's because there's more ocean in the southern hemisphere, so it holds more heat. And so if you were to average out all the temperatures, it's slightly warmer in the southern hemisphere. All right, I won't go, you can just read these. Any questions on the rest of these? Or if not, I'll just click to the next one. But you get the idea of the impact of continents and oceans. Now, as I said, the climate is a complex system. I showed you those 5 main factors that drive it. But because of the way the Earth surface, whether it's oceans or land surfaces, because they have all these living organisms in them, which in themselves are complex systems, and they're taking in whatever they need to survive, and they're giving off waste products. These are all part of the cycles that are part of the entire climate cycle. And it turns out that the links between certain aspects of the cycle or the climate system are more important than the individual components. And that's because if you have one component affecting another component, that component can affect other components. And the changes that occur just get spread through the whole system. And that's why, see down here I say slight changes to any part of the system. In other words, I showed you the Milankovitch cycles. Those are very slight changes in the orbit, very slight changes in solar radiation. But what they do is initiate changes that go out throughout the entire system. And they magnify, and they multiply their effects so that the entire system will be changed. Now, going back to what's caused the ice ages, when Milankovitch first came up with his idea that the orbital variations would cause the comings and goings of the ice, everybody laughed at him because they said, well, there's hardly any change. However, there was just enough change so that the oceans would warm up a little bit, say that there was more solar radiation coming in. If the oceans warm up a little bit, they give off CO2 into the atmosphere, the dissolved CO2 that's in the water. And that little bit of CO2 causes a little bit more warming. A little bit more warming causes more evaporation. More water vapor gets up there, more warming. And so you get this continuous, what's called a positive feedback loop, which eventually will cause enough warming to melt all the ice in an ice age. And then if you gradually have less solar radiation coming in because of the orbital variation going the other way, then you have a little bit of cooling, more CO2 is absorbed by the oceans, less water vapor is evaporated, the cooling continues. And pretty soon, you get ice forming. Now, it always takes longer for the ice to form than it does to melt it. So that's why if you come to the end of an ice age, it's a pretty dramatic shift from the ice age to the interglacial. And it takes 2 to 3 times longer to go from an interglacial to a full-blown ice age, because it takes that long for the freezing to occur. Okay. And here's, I already mentioned about feedbacks. The melting of the ice in the Arctic is a good example of a positive feedback, because the more melting of the ice you have, the more warming you're going to have, because you get open ocean. And the open ocean will absorb more solar radiation, et cetera, et cetera. Now, a negative feedback means, say you have evaporation like off the coast of California. And that evaporation will occur, but then you'll get low stratus clouds forming off the coast, and that'll stop the evaporation. And so you won't get any more warming. So that's called a negative feedback. So it's like, say you have a bowl, and you put a ball in it, and you put the ball over here, it's still inside the bowl, and the ball will just go back down to the bottom. But suppose you put the ball on the edge of the bowl. Now, if it's in the bowl, we call that a negative feedback, because it wants to go back down to the bottom of the bowl. That's the state that it wants to be in. If you put it up on the edge, and there's just enough to push it over the edge, it goes to a new state. That's a positive feedback. I don't know if does that make sense to you? So that's the difference between a positive feedback and a negative feedback. Positive feedback means the cycle will continue and accelerate, and you go to a new state. Negative feedback means it'll try to move to a new state, but it gets suppressed and it stays in the old state. Now, if as far as the climate's concerned, if the energy balance what comes in from the sun and what goes out to space, if it stays pretty even, then that's a negative feedback situation. If you have a change with more coming in, things going out, then you start having a positive feedback, and then you go to a new state. And that's where we're headed now, to a new state. And one more thing about the ice cores and what's been happening over the last, well, this goes back 400,000 years. And you can see the blue represents the CO2 concentration. The red represents the average global temperature. And you can see that they're pretty much in lockstep. So here are the interglacials. Notice how the interglacials, where the warm sections are pretty short. See, and this is the one we're in now. Whereas, and you can see where going from the coldest part down here up to the warmest part is fairly rapid compared to cooling off again. And it's the same sort of cycle every 100,000 years. Now, look what's been happening with the CO2 concentrations. See here, during this time, the CO2 concentrations varied from close to 300 parts per million to about 180 parts per million. 300 parts at the warmest time, 180 at the coldest time. But look where we are now. Well, this was 2008 when we were about 395. If this were extended to now, another 20 years, or another, what was that, 14? Yeah, 14 years, we'd be up here somewhere. We're up at 415 now. And the trends for CO2 concentrations just keep going up. Now this shows how the CO2 concentration, and they get this data from an ice core, this Law Dome, I think it was in Greenland. And you can see it's pretty even from 1,000 years ago up to about 1800. But after 1800, when the Industrial Revolution kicked in and industrialized farming became more widespread, look what starts to happen. And then just in the last, say, 50 years, it's just shot right up. And that's because of what we've been doing. All the activities, not only putting out all the effluents from internal combustion engines and power plants, but also from forest destruction. Because forests are some of the biggest absorbers of CO2 from the atmosphere. So if you get rid of forests, you get rid of a big sink for that CO2. So CO2 isn't going to go anywhere, it stays in the atmosphere. And this is the most recent, almost up to the present time. This goes, see, this was about 2018, I think, when I got this graph. So now, another 4 years, we're about up to here now. And that's from the Mauna Loa Observatory. In fact, that was the famous Keeling curve. It started in 1957 during the International Geophysical Year of that time. I really remember it because I was a big science nut when I was in grammar school, and that was a big deal when I was in the 6th, 7th grade. And so I remember when that started. And you can see the global temperature trend since the 1880s. A little bit of warming in the early part of the 20th century. But by 1980, there's definitely an upward spike. Now, you can see that year by year it can vary, but the trend is still up. Now, some of the effects of that warming trend, the Arctic sea ice. This is the extent, this would be 7 million square kilometers, and here you got 4 million square kilometers. So you can see just how much since 1980 has disappeared from the Arctic. In fact, I'll call it up in a little while when I get back to the present data. You can see just how fast the Arctic ice is melting this summer already. Here we are, not even the middle of July yet, or towards the middle of July, and a lot of it's already gone. 50 years ago, it still would have been completely ice covered. But now, I'd say about at least 20% of the Arctic Ocean is just open water. And another even more important factor in the Arctic is the volume of ice, the thickness of the ice. Back when the US and the Russians were playing games under the ice pack in the early 50s and 60s, during the time of the Cold War, they had all these submarine operations that would go under the Arctic Ocean ice pack. And both countries were reporting that the thickness of the ice near the North Pole and over most of the Arctic Basin was 50 feet, 100 feet thick. Now, most of that, what was called multi-year ice, is gone. Most of the ice that forms in the Arctic Ocean is just 1 or 2 years old, and then it melts, because it just doesn't stay cold enough in the summer anymore up there. So most of the ice that was there has melted when you look at the thickness of the ice. So figure back in the 1950s, the ice was this thick, now it's like this. And that's for the entire Arctic Basin. And the biggie, most of the heating that's occurred, and this is another thing most people don't realize, has been in the oceans. And you can see here, this is from 1960. And it really started taking off during the 1980s. And you can see just how much the oceans as a whole have warmed up. That's the ocean heat content in, I think, in joules, and 1 joule is about 4.5 calories. So each, I think every cubic meter, that's how much, so many calories every cubic meter. This is how much ocean heat content has gone up. Now, the atmosphere, all the weather that we're familiar with happens because the atmosphere circulates. We have 3 general circulation systems. It's the general circulation system, which is the entire atmosphere, and it's reflected in things like jet streams, Hadley cells, and trade winds, things like that. Then you have the secondary circulations, which are low pressure systems, high pressure systems, which are more regional. And then you have the tertiary circulation systems, be like a sea breeze, or if you live on a big lake, it'd be a lake breeze. And this shows an idealized picture of how the atmosphere circulates in a general sense. Now these purple lines are all in the upper atmosphere. Say you go up to about 30,000 feet up. That's where the jet stream is. And you can see in both hemispheres, the fatter purple lines represent where the jet stream would be. And same thing in the southern hemisphere. Now, I put that up there just to give you a general idea of where the polar jet stream usually is. And also notice this would be a vertical cross-section. See, most of the heating takes place at the equator, so you have updraft here. The air wants to go towards the pole, and it wants to come back towards the equator on the surface. And that's what causes our weather, this shifting of the Earth, or the air on the Earth. Now, if you look down at the North Pole, and you have a cold Arctic, the jet stream tends to be fairly smooth with little bulges here and there. And that's the way it used to be. Now, if you have something like this, you have a cold surge coming down here. Something like this would be a warmer surge going there, but nothing too extreme. Occasionally, you get more of a dip here and there, but on the average, things were fairly smooth. You get systems going through, and you get something, maybe rain or snow, and then it'd move on, and you get dryness and clear skies, and then another one would come by, and things would move. However, as the Arctic warms up, look what's happening to the jet stream. It's getting sluggish, and you're getting these big dips and rises. Now, see this right here? This means that very warm air would penetrate way up to the north, towards the pole. This means that very cold air would penetrate far to the south. So you get more extremes. You get longer cold waves in the winter. Even though the maximum or the minimum temperature isn't as cold as it used to be, you can still get longer cold waves. So instead of having very cold conditions for 3 or 4 days, you might have it for 2 weeks or even longer. And the same goes for warm spells. When this happens in the summer, you can get roasted the way they're doing in the west this summer. Nothing has been moving out west. It just continues to be hot and dry, and their drought conditions are getting worse and worse. And that's because the jet stream has stalled. If, say this is North America right here, see where it goes up here? That would be the west, and this would be the east. So we're relatively cooler than the west, even though all things being equal, we've still been pretty warm. June was slightly cooler than usual, mainly on the mins. Did you see the June climatology that I sent?
I probably did at the time, but,
okay.
I'm not sure. Right.
Did you see it, Pat?
I think I did, but
All
I
right.
don't remember.
Well, the reason I'm asking is because Sam Brown usually sends it to his dat list, and he didn't send it this time. So I'm wondering if because of my computer problems, it didn't get sent out. So yeah, when I get home, I'm gonna resend it.
Okay.
So that's the June climatology for this area. So anyway, that's what's causing extreme conditions. Now, when things were more smooth, we call it zonal, this would be the way the jet stream would be. In the winter, the polar jet stream would usually do this. So you can see where New England is usually on the colder side, and the west tends to be a little bit warmer. Occasionally it'll dip down like this a little bit and we warm up, but overall, that's the way it usually was. And there's also what's called a subtropical jet stream that forms in the winter. And this is what can bring tropical air up and feed big storms when they occur. But that, if this were a weather course, I'd get more into it, but it's not so. Now, if you have a very sluggish jet stream, look what's happening. Okay? Again, nothing moves here, nothing moves there. If you have a storm that follows the jet stream, it'll blow up here someplace, and we could get 2-3 feet of snow out of something that, if you have a pattern like that form here in New England. Now in the summer, again, the zonal jet stream, a lot weaker, but more or less goes like that, across the country. And most of the air that comes in off the Pacific dries out over the Sierras and the Rockies. And so even though it can get very warm, it's very dry out here. Whereas most of the air that comes over the east comes out of the Gulf of Mexico, moves like that. And that's a pretty, or it used to be a pretty typical summer pattern. However, again, with a very weak and sluggish jet stream, you get those big up and down loops. Things get stuck, nothing moves, and you tend to be a lot warmer further north. And even the cooler parts, just like I said a few minutes ago, even here in New England, if we happen to be on the cool side of this pattern, it's still not that cool, because there isn't much cold air in the Arctic right now. And there hasn't been for a few years now. Now here in Maine, the main climate drivers, mainly it's because of our geographic location, where we are in North America. We're right smack dab in the middle, 45 degrees approximately, it goes right through the middle of the state. And we're on the east coast of a major continent. And that means the air masses tend to come out of the continent, which means that they'll be more extreme. So that's why we tend to have relatively cold winters and relatively warm summers, because most of our air comes off the continent rather than off the ocean. Occasionally we will get ocean air in, but it's only if a storm goes by. Now if we were on the west coast, like say we lived in Portland, Oregon, well, because most of the air comes in off the Pacific, they tend to have a much milder climate. It's milder in the winter, cooler in the summer. I remember when I first went to Monterey, I left New York, Kennedy Airport, it was about 95 out, it was the end of June, and I'm going out west and I'm looking down at the surface as we're flying along. It's the first time I've been in a plane. And we landed in Monterey, and it was only about 65. It was clear, and it was sunny, but it was only 65 because the wind was coming in off the Pacific. And that was my first introduction to where you are on the continent affecting the kind of climate you have.
Right.
If you live in Monterey or any place else along the west coast, you tend to have a much milder climate because the air tends to come in off the Pacific. Same thing if you're in West Africa and Europe. The air tends to come in off the Atlantic, so that's why they have a mild climate, especially compared to here. You know, when the English settlers came over, they couldn't believe how cold it got here in the winter, because they never saw that back in England, because most of the air comes in off the Atlantic there. Now, we do have a mountain range to our west and northwest, and whenever the sky's clear, you can look up that way and see them. And a lot of times they'll act as a barrier to Canadian air coming in. But because they're not that high, it's not a real strict barrier. But it does have some kind of an effect. And we do have many hills and valleys, so that'll affect the local conditions. For example, a lot of people, they know if they're in a valley, and they tend to have frost more often than people that are up on a hill. And we have a relatively cold ocean to the east. And that cold ocean has a big bearing on where storm systems will go and what the effects here in Maine will be. Because as it pulls air in off the ocean, let's say we were in New York and the air came in off the ocean, it'd be mild, because the ocean water down there south of Long Island is a lot warmer than it is here in the Gulf of Maine. But because we have the Labrador current that comes down along Nova Scotia into the Gulf of Maine and up into the Bay of Fundy, have you ever been swimming off Roque Bluffs near Machias? That water is cold. And it's because it's the Labrador current comes right in there. It's the coldest part of the Gulf of Maine. And that has a bearing on what happens whenever a storm goes by. Also, we have many different types of air masses. Right now, the air mass that's over us is kind of halfway between a tropical air mass and a polar air mass. So that means that it's kind of in between as far as humidity goes. But we can have a very dry air mass coming out of Canada or coming out of the plains, or we can have a very humid air mass coming up from the Gulf of Mexico. And also a humid air mass coming in off the Atlantic. And this part of New England, or this part of the Northeast, is actually a convergence point for storm systems which come across the country. So it doesn't matter if they're coming from Alberta, across the Great Lakes to Maine, they'll come that way, or they'll come from Colorado and through the Ohio Valley and up to Maine, or they'll dip down into the Gulf of Mexico, come up along the Appalachians or along the eastern seaboard, and also hit Maine. So we'll get hit with low pressure systems from just about anywhere. And there's that Labrador current I was telling you about. See, it comes around Nova Scotia, goes back up into the Bay of Fundy, and it moderates a little bit as it heads closer to Portland, but still, it's a lot colder than it would be if we didn't have that Labrador current coming in. But one note is that over the last 10 to 15 years, even as the Labrador current continues to come down and circulate into the Gulf of Maine, because the water up in the Arctic has warmed, that Labrador current is not as cold as it used to be. So you might have gone swimming with 50-degree water 20 years ago, if you go to Road Bluffs.
I don't think so, but anyway.
I say you might.
No.
Now, it might be 60,
No, still
which
not.
that's still 10 degrees warmer. And it's been shown over the last year or two that the Gulf of Maine is warming up faster than just about any other body of water on the planet. And the reason for that is because the Arctic itself is warming up. And there's more heat in the ocean, so the Labrador current is not as cold as it used to be. Now, here's that summary of effects that we can expect to see. Generally milder, cloudier nights and winters. And I think you'll have to agree that's what we've been seeing. I remember when we first moved to Garland in 1982, and you could see the Milky Way at least half the nights because the sky was so clear. Now, if you see the Milky Way 2 or 3 times a year, you're lucky, at least from our house, because it's just so cloudy and the air tends to be more humid. And if the air is more humid, you don't get that real crystal clear atmosphere that you get if it's very dry. We also get heavier rain and snow events. And the storms tend to be larger and they last longer. Even though we can go through periods where they don't show up and they keep missing us, so we end up with a drought, but when they do come, we get just the opposite. And that's going to be the trend as time goes on. More frequent and longer heat waves in summer with higher humidity. And we've seen that over the last few years. Relatively fewer but longer cold waves in winter with higher min temperatures than in the past. Again, going back 40 years when we first came here, it was at least 2-3 times a year we get down into the minus 30s in January, February. Never see that anymore. The coldest I've seen in the last 10 years is around minus 20. And it doesn't even get into the minus 20s. It's just about touching minus 20. And there were some years, it was about 2 or 3 years ago, we never got below minus 10. So that's southern New England weather. That's not Maine weather. Of course, they're getting more like New Jersey now down there. Greater variability all year, especially in the spring and the fall, because those are the 2 transition seasons when the patterns shift from summer to winter. So when you have a lot of variability, it was about 3 years ago, we had a heat wave in May where we got up in the 90s, and then the 1st of June we had frost. Now those types of things are possible when you have a lot of variability, with wild swings in the jet stream. And a general tendency for more clouds in all seasons, and that's because more, as the oceans and the atmosphere warm, you get more evaporation, More moisture in the atmosphere, more clouds. And drier periods will tend to be drier, and wetter periods will tend to be wetter. Again, it has to do with the jet stream getting stuck. If you're in this pattern with the dry air coming down from the middle of the continent, you're going to be in a drought. If you're in this pattern, you're going to be in a flood situation. It all depends which side you're on. That's why you can have a drought here and a flood here at the same time. Tendency for extended warmth into the fall, especially here in New England, and longer and milder thaws in the winter. So you've probably experienced, maybe you go 2-3 weeks, it gets above freezing just about every day. Now for this part of the world, that's warm in January. In fact, sometimes it gets up in the 40s, close to 50. That's time to take your shirt off and put your shorts on. Now, a tendency for more rain and freezing rain in winter and gradually less dependable ice on the ponds, lakes, and streams. And again, I think everybody can agree that's what we've been seeing. And we were talking about it at the beginning about the crappy winter we had last year with all the ice. Even after we had snow on top, the ice formed and it stayed there because it got insulated with the snow on top. And so if you dug down, you could see about 3 or 4 layers of ice. Now that's bad for like deer. It can hurt their hoofs. You know, they cut themselves as they go through the ice. And other animals that depend on fluffy snow for their survival. In fact, up in Alaska, the caribou are having a tough time because they're getting more rain in the winter up there. And so they're getting the same situation with the ice crusts forming up there. And so the caribou are having a tough time finding the lichens that they need to find during the winter. Extended dry spells, even severe droughts, alternating very wet periods, we already covered that. And more severe coastal storms in all seasons. And this includes hurricanes when they do form. Now, the data shows that hurricanes haven't been increasing in frequency. They still tend to follow cycles from year to year depending on the overall configuration of the atmosphere and the oceans. However, over the last 10 to 20 years, the intensity of hurricanes has gone up. Where we used to get Category 5 maybe once every 1 to 3 years, now we've had years where we've had 3 or 4 Category 5s just in one season. And that's because the oceans, having warmed up as much as they have, there's more fuel to have explosive deepening and strengthening of the hurricanes. When, was it Irma? I forget the names. But anyway, there was just one recently, I think it was 2 or 3 years ago in the Gulf. It started off as just a tropical storm near Miami, went into the Gulf, blew up, became a Category 5 before it hit the Gulf Coast. And that's happening more and more often. And a generally longer frost-free period, but still you can have an untimely frost on both ends, as we had 2 years ago with that frost in June, after a heat wave in May. Now, I just wanted, this was the picture that I put on my forecast this morning. For Pat and Kim, you know how that works. And I just wanted to show you there was a very weak low pressure system down off Long Island this morning. And so see these green spots, those are areas of rain that kind of moved along. And then there was this instability trough coming through from Quebec, and that's what's giving us the clouds right now and the potential for a shower or thunderstorm. Because there's an upper air dip in the jet stream right here. And that still has to move through, and it'll take until tomorrow for that to go all the way through. So that's why conditions will be a little bit unsettled. But because of the general flow is this way, there isn't that much moisture. So that's why whether we get anything out of this is very iffy.
Right.
Because if you don't have a lot of moisture, you just got to be lucky to get anything.
Yeah.
And then you can see there's a big high-pressure system over upper Michigan. And that's going to be slowly moving this way. So by tomorrow, it should start being really nice again, and right into the weekend. And then that high pressure is going to come down this way, merge with this one, and guess what's coming back on Sunday afternoon? More heat and humidity. And then Monday, maybe another, see this front out here? That might be reaching us by then. So I just thought I'd throw that up just to give you an idea what's going on right now.
Yeah, we might want to see if anyone has any questions.
Yeah, that's,
Yep.
right now,
Yep.
rest of the time, it's up to you.
Yep. Anybody, any weather-related or climate change or anything he's talked about, feel free to ask anything.
I have a question.
Yep.
Every night when I'm doing dishes, I have this window that faces northwest.
All right.
Beautiful sunsets and clouds and all. Well, it was a couple of days ago, I think, we were supposed to have it's Tuesday, we were supposed to have severe storms. They were forecasted. And I saw these really, really dark clouds. It's probably like 7:30 at night.
Oh, this was Tuesday night?
Okay.
Yeah, I remember that.
Okay, so it was coming right for us. I said, oh, the government must be getting it now because I can, it's that direction. As it came close, the clouds were right almost on us. And as they came on us, they split
Mm.
and went around us.
Yeah, that surprised me,
No.
because the same thing happened at my place in Garland. Because I was at a planning board meeting at the town office, at the old school there. And we came out the door and we looked up to the northwest and it was black.
Yeah.
And I thought, looks like we're gonna get something. By the time I got home, the same thing that you saw, it just opened right up and it got bright again. And to me, that means, because I was trying to look at the edge of the clouds, and I didn't see a very high vertical extent of the clouds. And I wasn't sure if it was because I didn't have the right angle to see it, or if they actually were not very high. So they were thick enough, and because the sun was low anyway, that they were thick enough to block most of the sun's light, but they weren't high enough to really give you something.
Oh,
See, in order to get a real good thunderstorm, you've got to have a tremendous vertical
Yeah.
development,
sure.
because it's going to get way up there and poke into the stratosphere. And if it doesn't, you're not going to get very much. And we didn't get anything.
No, we didn't get anything either. And that happens, I see that happen, not splitting, but it seems like the clouds, you think they're going to come right at us, they all go north.
Mm.
Is it because the wind changes or?
Yeah, the jet stream over us the last, say, 3 or 4 days has tended, let me get back to, this is easier to show it if I got a map. See, the jet stream has been more or less doing this. So, see, over New England, there's a little bit of a southwest component that would take most of those up towards the Worcester County rather than here. So that's why, if you're in Jackman, you're probably sick of the rain, because they've been having one shower after another.
Oh,
Same thing up towards Caribou and Madawaska and those places. But here, because everything's missing us and then going up towards that area, we don't get anything. And our drought gets worse.
Yes, sir. Yeah.
Yeah. And right now, it's because that's the way the jet stream is. And as that jet stream moves over so that the flow gets more like that, we're going to get into that dry period starting tomorrow right through Saturday. And then this other dip here will be moving over so that by Sunday, we'll be back into that type of a pattern. Any other questions?
Where does the water that forms the ice in the Arctic and the Antarctic come from?
The oceans. In other words, let me see if I can get a picture of. I'm gonna- Oh, yeah, one thing I wanted to show you. Where the ice is right now. Okay. Now you'll notice that the Arctic region here, there's an opening here to the Pacific through the Bering Strait, and a big opening to the Atlantic through the Denmark Strait, the Fram Strait, and just this part of the North Atlantic. And when storms come across the North Pacific, they bring that moisture into the Arctic. When they come off North America and up into the Arctic, they bring that moisture with them. So all the snow that forms and falls in the Arctic is from migrating storms that come in off both the Atlantic and the Pacific.
My question, I guess, wasn't very articulate, because what I was driving at was, is all that snow and ice up there come from snow descending, or is it frozen seawater?
The actual, the pack ice, that's frozen seawater. When the storms, during the winter, say like from mid-fall through early spring, the storms that come over them will dump snow on top of that frozen ice. And that'll cause, it'll get compressed, or it used to get compressed year by year because it wouldn't melt during the summer. And that's why, remember I said back in the 50s, the ice was so thick, and now it's not. So now, when that snow falls during the winter on top of the ice, and you get into May and June, it melts very rapidly. Especially this year, it's really been going fast. You can see already that the so-called Northeast Passage along the coast of Siberia is almost opened up all the way. Now, 20, 30 years ago, that was unheard of. Pretty soon, you'll have the Northwest Passage opening up this way. Usually, because it's been a lot warmer in Siberia than in Canada, the Northeast Passage opens up first, and it lasts longer into the fall than the Northwest Passage.
So I should sell my Panama Canal stock.
Yeah, a lot of the Arctic countries have already been banking on an open Arctic for the transportation.
To get back to the source of the ice, if you drilled a core down through the snow that has built up and melted and then built up more snow, will you eventually get to ice that tastes salty? I don't know, does it get cold? Is there
Yeah, most of the ice
there that's cold enough to freeze salt water?
Yeah. The temperature for most salt water, it's about 27, 28 Fahrenheit. If it gets that cold, then salt water will freeze. If it's multi-year ice, in other words, ice that's been there and not melted for a few years, that salt will migrate out of it and becomes fresh. That's why a lot of the multi-year ice is almost good enough to drink, because the salt had migrated out of it. In fact, you go to the Antarctic, where the ice has been there for thousands of years, millions of years, most of that is drinkable.
Because it used to have salt in it, but now it's hydrated.
Yeah, on the ocean. The stuff that's on the land, that's always been drinkable. But the ice shelves that formed off the Antarctic coast, some of those 200 feet high, and they're even thicker underneath, under the ocean. And the ones that have been there for a long time, that's all pure water or pure ice. The salt is migrated out except where the ocean water is lapping against it. All right. In fact, let me flip that over. Go to the South Pole. Yeah. Yeah. Okay. Now, they're getting into their winter. And look what you notice here. The extent of the ice around Antarctica used to be a lot further by this time of the year. Look here at the Antarctic Peninsula. It's almost ice-free. And in fact, the Antarctic Peninsula has been one of the warmest, or the rapidly warming places on Earth. They hit a record high temperature for Antarctica, I think it was 2 summers, or their summer, where it got up to 70, which is amazing. True, it's sticking up towards South America, but still, it used to be that the whole peninsula here was always locked in with ice. But now, because of the melting that's been going on around the edge of Antarctica, even in their winter, it's not the way it used to be. And there's another, let's see if I get my orientation right here. Yeah, over, that's McMurdo. No, that's McMurdo. So, I forgot where it is, but there are 2 glaciers, the Thwaites Glacier and the Pine Island Glacier. I think they're over here. And those 2 glaciers really have glaciologists and climatologists worried because it looks like they're about ready to give way. The ice shelves that have been holding them up have been disintegrating from underneath because the ocean water around Antarctica has warmed up so much. And so if those ice shelves give way and the glaciers start to flow, they'll go into the ocean, and over the next 20, 30, 40 years, sea levels will go up maybe a few more feet because there's that much water in those glaciers. All right. Anything else?
What about the glaciers in Alaska? Are those melting?
Yeah. Most glaciers on Earth are melting. There are a few local situations where they've had more snow, for example, during the winter, that they've been able to maybe increase the glaciers. But those are a minority, definite minority. Most glaciers around the world are shrinking. In fact, the glaciers in Montana, the Glacier National Park, the rangers there, they're worried in the next 20, 30 years there won't be any more glaciers left. They'll have to change the name of the park. And the biggest worry right now is in the Himalayas, because a lot of people in both China and India depend on those glaciers in the Himalayas for their drinking water and for irrigation and things like that.
Speaking of change, have you run across a group that was trying to predict the relative positive versus negative changes of climate change in all the counties in the United States?
Yeah, I saw that. Yeah, somebody pointed that out to me. It was about a month ago, I think I saw that. And you could go county by county and see how the changes.
The reason it's relevant here, I can't quote it exactly, but the reason it's relevant to us is that there are some 3,200 and something counties in the United States and its territories. And they looked at 10 different categories of, storms, drought,
Right.
floods, crime, etc. 10 different categories and rated them sort of positive and negative for overall change. And Piscataquis County was number 5.
Yeah.
Of the
Yep, I
entire
remember seeing that.
3,200.
That's
So
great.
don't sell your land.
Oh.
Everybody's gonna be coming.
Yeah.
For positive, you mean though?
Yeah,
Oh, okay.
we will suffer the least.
Right.
Oh,
is
that's
that
right,
right?
okay.
Yeah.
But we'll have the more positive effect.
Yeah.
You'll be able, the farming will get better.
Oh,
Oh.
there it's coming.
Oh.
Right. In fact, now that you mention, I remember, I don't know if, you know Fred Bever, one of the reporters for NPR,
Yeah.
Maine Public Radio. He called me up because I guess Leslie Furno told him, because he was asking him, he saw that study,
Yep.
and he got in contact with her somehow. And she said, well, ask Ed Hummel. If anybody around here knows, he would know. So he called me up and he wanted to know what I thought some of the changes would be for this area. And I said, well, the usual ones, but I think one that most people don't really think about is an influx of climate refugees. And he put that on the news that night.
Oh,
Wow.
So I don't know how many people heard
They
that.
say all the states that are contiguous with the Canadian border
Yeah.
will have a relatively positive effect compared to, so the border, the difference is at the 42nd parallel.
Right.
Oh.
So
Yeah, south of there, it's gonna be drought.
intolerable.
Yeah. And in the southeast, the humidity is gonna get so high that it would be uninhabitable. And in the southwest, it'd just be too dry to do anything. And, Colorado River is already drying up,
Mm.
and they're still, I don't know if it was on 60 Minutes or one of those programs, they had this segment that there's, in Arizona, there are still real estate people that are pushing for new developments in the Phoenix area. And the reporter was just shaking his head and said, I don't know where the water's coming from.
Yeah.
Well, thank you, that was very
Yeah,
good.
Yeah, that
thank
was
you
very
very much, Ed.
Thank
Definitely knowledgeable in all of that. That's-
Yeah, but I wish I had
Thank you for
more
sharing.